Well, welcome BC students to our second video regarding limits. Last night we approached them graphically and we got a really nice visual image of what the limit was measuring, and we talked about how it was measuring the intended height as opposed to its actual height and all that jazz. Well, tonight we're going to take a totally different approach and we're going to find limits analytically. It's kind of a funny word. A lot of times I'll use the word algebraically, or basically think anything that's not graphically kind of falls into the category of analytically. So we're going to break our video into 4 different mini lessons. The first one, we're going to look at limits with removable discontinuities. And anytime we talk about that, I want you to just think of holes. We're going to get everything factored, cancel out the hole, and so forth. Then we're going to do some non-removable discontinuities, and I want you to think of vertical asymptotes in that case. Limits as x approaches infinity, I want you to think of horizontal asymptotes. And then last but not least, we're going to tackle some piecewise functions, and that just boils down to some really crazy looking graphs and being able to find the limits without having to draw the graph itself. Now, just before we go too far and get into some really crazy limits, I want to make sure that we don't overlook the obvious. In fact, we're going to talk about a method called direct substitution. And this actually works probably on a majority of the math problems. The only problem is the AP is not going to settle for that just because it's so simple. But just in case they do, here's our first example tonight. Let's consider the limit as x approaches 2, and the function is going to be x plus 7 all over x squared minus 1. So we've got ourselves a nice rational function here. And notice if you just do a direct sub and plug that 2 in right now, you're going to get 9 over 1. So the intended height of that function is going to be a 9, and that's it. It just worked out beautifully. Let's take a look at another one. That was so hard I thought we'd enjoy another one. Limit as x approaches -1, and let's try the rational function x squared plus x all over x minus 5. Now something a little peculiar happens here. My numerator turns out to be a 0 when I just do a direct sub, plug the -1 in for these x's right here. On the bottom, I'm getting -6. Now in this case, this is actually legit. 0 divided by any number is actually 0, so 0 is the intended height. What we're going to get into here in a few short moments is we're going to take a look at what happens if I get 0 divided by 0 and why that's a totally different case. But if you do get 0 divided by a regular finite number like we did here with the -6, then the answer actually is 0 itself. So as we said moments ago, we're always going to try direct substitution first. So always try that first. But like we said, on the AP exam, there's probably a 99% chance that that's not going to work. And if that doesn't work, we're going to really get creative. We might be doing some factoring if possible. And then, of course, if you factor it, you go ahead and simplify it. Hopefully things cancel. Or maybe you're going to do something weird like multiply the top and bottom by the conjugate of the denominator. Just all sorts of weird math tricks that we're going to train ourselves to look for. And the first one I want to try is this particular limit right here. Limit as x approaches 4. 3x minus 12 is our numerator. 2 minus radical x is our denominator. So we'll go ahead and we'll try that direct substitution because that's what we're going to try first every single time. And let's see, my numerator turns out to be 12 minus 12, which is indeed 0. Thinking, okay, I still got a chance. As long as the denominator is an actual finite number other than 0, we're going to be in good shape. But the problem is it does turn out to be 0. And this is what we call indeterminate form. Or in other words, we are unable to determine what the value of the limit is. And what that means is we basically hit a dead end. We got to back up and go try something else. So here's one of those jobs. I'm going to jump on the conjugate. And what I'm going to do is I'm going to multiply the top and the bottom by the conjugate of the denominator, which in this case is going to be 2 plus radical x. And of course, whatever I do to the top, I'm going to follow that up by doing it to the bottom to make it a legal move. And I'm not going to waste my time foiling the top, and I think you're going to find that advantageous. Just leave it as the product of I'm going to factor out the 3. That'll give me x minus 4. And then we've got our 2 plus radical x. So I factored the numerator, left it all as the product of all that jazz. On the bottom, though, I am going to multiply them out. And 2 times 2 is 4. I'm foiling. The outer and the inners will cancel. And last times last would be minus x. So what's going to happen here, something really great is going to happen. We're going to cancel these, but the order was reversed, so we'll negate the 3. Now we have a more simplified limit to work with, and we're just going to plug that 4 straight in right now. So let's see what we got. If I do plug the 4 in right now, let's see, 2 plus 2 is 4 times -3. I'm thinking -12 is the value of my limit. Okay, so now we're going to start to get into the really good stuff, and we're going to take a look at some removable discontinuities, and we kind of gave it away at the beginning of the video, and we said removable discontinuities are like holes. Now, the reason they're removable is the fact that by the time we get everything factored and canceled out, we're basically removing the hole. And so what we see here is if we did start with a direct substitution on our fourth example, we would indeed get 0 for a numerator divided by 0. So boom, indeterminate. Like I told you, I think that's going to happen 99, if not more, % of the time on the AP exam. So what we're going to do is we're going to go ahead and factor that numerator. And let's see, x times the quantity x squared minus 3 divided by x. Boom, right there's that cancellation. So what we've proven is there's a hole at x equals 0. Now the resulting equation looks like this, x squared minus 3. And what's really important to understand is that the original one and my new simplified function, these guys are equivalent. The only difference is this first one up here had a restricted domain. X wasn't allowed to be 0. Whereas this new one down here has an unrestricted domain. The domain is all real numbers. So at this point, it's just as simple as plugging in that 0. And I think we're going to get an answer of -3 is the intended height of that graph. If we were to graph the original function here, basically what we're getting is a parabola. And then right at the vertex at -3, there would be that hole. And then it would continue up like this. And so what we're saying is, yes, when x equals 0 down here, the curve has an intended height of -3. All right, phase 2 here, we're going to look at limits as we deal with non-removable discontinuities, in other words, vertical asymptotes. There's very little factoring that can be done, and even if you can factor, it doesn't really lead to any cancellations, therefore they're non-removable. We're just kind of stuck with them. We got to deal with them. And so what we deal here with example number 5 is even though the denominator does factor, it doesn't cancel with anything in the numerator, so we're stuck with it. But by analyzing the denominator and setting it equal to 0, we've discovered that there's 2 vertical asymptotes, one at +3 and one at -3. And then also, just a real quick recap, if we were to graph this function, and we'll say there's 1, 2, and 3, so we'll put a vertical asymptote there. -1, -2, -3, we'll put another vertical asymptote right there. There also happens to be a horizontal asymptote at y equals 0. Just we see a small over large power fight. So I'll go ahead and slide that asymptote in there. Now at this stage of the game, there's different possibilities here. One of 2 things could happen. In between the vertical asymptotes here, we're either getting a parabola that opens up or you're getting one that opens down. In other words, you're getting kind of a parabola that's either entirely above the horizontal asymptote or you're getting one that's entirely below. It's one of 2 things. And our question is, are we getting case 1 or are we getting case 2? See, let's go back to that original question. We're trying to find the limit as x approaches 3 from the left side, okay? So I'm saying I'm right in here. This is just to the left of +3. And I want to know, is the graph approaching positive infinity or is the graph approaching negative infinity? See, you really only have 2 choices because when we know that the vertical asymptote exists, there's only one of 2 things that could happen. The graph's either extending infinitely up or extending infinitely down. Now, how do we decide which is which? What we're going to do is we're going to pick a random number that sits just to the left of 3, and I think x equals 2 would be a great candidate. And by plugging in a +2 into this function right here, we're going to decide whether the graph is above or below that horizontal asymptote. So let's go ahead here. If we want to figure out what f of 2 is, I get 2 plus 4 is 6, 4 minus 9 is -5. Now, because this is a negative value, it's putting us in this neighborhood right here, which clinches the fact that the graph is extending infinitely downward. Therefore, the limit equals -infinity, and just because we're heading south. Let's go ahead and we'll try one more just to make sure we got this. So I want to go ahead and try one more example where we have a non-removable discontinuity. So let's take a look at the limit as x approaches 5 from the right side this time of the function, let's say 2x over x minus 5. So again, there's no cancellations, there's no removable discontinuities, but we do know that there's a vertical asymptote at x equals positive 5, and we do know there's a horizontal asymptote at, let's see, power fight, look at the coefficients, y equals 2. So as we set up our graph, it's starting to look like this. Let's see, 1, 2, 3, 4, 5. Throw that vertical asymptote in there. 1, 2, we got a nice horizontal asymptote. And here's what's happening here. The graph is going, again, it's going to do one of two things on the right side of the 5. It's either going to start this way and then extend infinitely up, or it's going to start this way and extend infinitely down. Now, obviously, both things can't happen. Otherwise, we wouldn't pass the vertical line test. So it's got to be one or the other. And how do we decide whether it should be case number 1 or case number 2? Well, we're going to pick a number that sits just to the right of 5. We'll say, how about x equals 6? Doesn't that look like a great choice? And so I'm going to plug in and evaluate f of 6, and that's going to give me a 12. Let's see, equal sign there. All over 6 minus 5 is a 1. So now because this is a positive number that sits above the horizontal asymptote, it says it's definitely this one, not this one. And this graph here is extending infinitely up, so the limit has a value of positive infinity. Now for our feistiest section, I believe, of the 4 tonight, we're going to talk about limit as x approaches infinity. In other words, we're going to ask ourselves, okay, what happens if the graph extends infinitely to the right? What kind of behavior is the graph exhibiting? Or if we extend infinitely to the left, what kind of behavior is the graphic exhibiting way out here? And that's where I want to go ahead and make an adjustment. Let's say plus or minus infinity. We're going to analyze both ends of the graph here tonight. Now, these have traditionally, up until this point, been the easiest problems we've ever done, because when we talk about limits as x approaches infinity, we're all about that power fight, where we compare the degree of the numerator to the degree of the denominator. If we have small over large, the answer is going to be 0. That's going to be true whether x approaches positive infinity or whether x approaches negative infinity. That's always our favorite one, small over large. It just doesn't get any better than that. The other case that we might run into, well, I'll skip to the third one. If it's large over small, again, the answer is always going to be infinity. The only difference is it could be positive or negative, and that's where we're going to talk a little bit about how to determine which one it is. And of course, if we have to go to the coefficients where we have same over same and we're dividing those coefficients, again, we've really got to have to watch our signs tonight. And that's really the point of including this in the video tonight. It's just a few extra tricks that the BC exam may throw at us. For our 7th example tonight, we're going to find both the limit as x approaches positive infinity and the limit as x approaches negative infinity. Now, for all intents and purposes, what we're really doing is finding all possible horizontal asymptotes for this function right here. Now remember, at most, a function can possess 2 horizontal asymptotes. Now, that's a fairly rare phenomena, but it is possible, and that's what we're going to see on this example here, and it's very similar to one of the problems we saw in our summer assignment. So again, one of my favorite things about doing limits as x approaches either positive or negative infinity is the fact that we could disregard all insignificant terms. Now when you look at the numerator, the lesser term is the 6x, so we're just going to disregard him. Because in the big picture, once x gets to the billions and beyond, 6x is really insignificant compared to the x squared, and it has a minimal effect on the graph. And of course on the bottom we'll disregard the plus 1 because he's the most insignificant term there. As we simplify this function, we're going to get plus or minus x all over 6x. And of course, that simplifies to plus or minus 1/6. So we know there's a horizontal asymptote at 1/6 and another horizontal asymptote at negative 1/6. But which one's which? Like, you know, if we said there's an asymptote here and then there's one here, basically we're trying to decide, does the graph go like this, or does the graph go more like this? And that's our challenge that we're going to try to figure out right now. So here's how we're going to do it. First things first, we'll start with the positive infinity. What's going to happen here is when I plug that positive infinity in and I square it, I'm staying positive and I'm getting a lot bigger. In other words, my numerator is going to be positive, and then on the bottom, 6 times infinity would also be positive, which is giving me positive 1/6. Now the limit as x approaches negative infinity, whoops, let's get that negative in there. This time, when I plug a negative, let's pretend we're plugging in negative 1 billion. Squaring it's going to make it positive, so your numerator just became positive. But on the bottom, 6 times negative a billion would be a negative number. Positive divided by negative that's where you're getting the negative 1/6. So it's just important that we're able to decide that it does indeed behave like this one right here, where the right side's approaching positive 1/6 and the left side's approaching negative 1/6. All right, we'll do one more in this category, and this is perhaps one of my favorite ones of all time. This is just a really cool problem. And again, it's a very rare function in that, and I'll kind of let the cat out of the bag now, there is going to be 2 different horizontal asymptotes, and that's why it's so important when they do ask to find horizontal asymptotes to analyze both limits, both at positive and negative infinity. But here it is. This function is not your typical polynomial. It's more of an exponential function, and we'll say 3 to the x plus 5 all over 6 minus 3 to the x. And so here's our crazy looking function, and we'll go ahead and we'll find both limits here. And the limit as x approaches positive infinity, and we're going to disregard what we feel are the insignificant terms. You know, in the big picture, this plus 5 is really insignificant and the 6 is really insignificant. So we've disregarded those. And as we evaluate this, just simply simplifying it, we're going to get negative 1. So in other words, y equals negative 1 is one of the horizontal asymptotes. Now as we check out the other end of the graph, and the far extreme left side of the graph, something really weird's happening here. And I'm going to go and try to go in slow motion here. We'll say 3 raised to the negative infinity. In other words, I'm kind of doing a direct substitution with infinity, which is, you know, a rather peculiar thing to do, but I think it'll drive home our point. Now, anytime you take a number such as 3 and raise it to a negative power, what you're really doing is creating an or a fraction, I should say. So it's like 1 over 3 to the infinity plus 5. And then 6 minus 1 over 3 to the infinity. Now what you'll notice here as we analyze just this particular fraction, of course 3 raised to infinity is huge. So 1 divided by a really, really, really large number is basically 0. So this whole thing is a 0. And same thing here, that's in 0. And so 0 plus 5 is really 5, and 6 minus 0 is really 6. So what we just proved is that y equals 5/6 is the second horizontal asymptote, so there is 2 different ones. All right, we've made it to our 4th and final topic for tonight, and we're going to look at piecewise functions and how to evaluate these limits without investing all the time that it would take to draw the graph. So we really want to try to wean ourselves away from the graph, so to speak, and let's take a look at a particular piecewise function here. Whoa, that might be the worst squiggly bracket ever. Let's see, 6 plus x as long as x is less than 3, and then we'll use the function 16 minus x squared as long as x is greater than or equal to the 3. And so what we want to do here is they're going to ask us what is the limit as x approaches 3 from the left side of f of x. And so the less than sign is always going to describe what lies to the left of the 3. And so just a real quick, we'll write this out. Less than means left, and I like that because they both start with the letter L. Less than and left. So what I'm going to do is I'm just going to use this function right here. I'm going to plug the 3 directly into that function. And that's going to give me radical 9, which is 3. So as x gets closer and closer to 3 from the left side, the function is approaching a height of 3. We'll check the other side out, limit as x approaches 3 from the right. And so now anytime we deal with the right-hand side of the graph, we want to focus on the greater than sign. This equal sign really has no bearing, pretty much ignoring that for right now. It's just all about the greater than sign. And we'll plug the 3 directly into this function right here. 16 minus 9 is going to give me a 7. So the intended height would be a 7. Now what we've just proven right there is because those one-sided limits didn't yield the same value, we would then conclude that the general limit as x approaches 3 period does not exist. And really what we've proven, because these two values were different, we've proven that the function is not continuous, but that's a discussion for another night. Okay, our very last example for tonight, and I'm going to do a couple with you, and then I'm going to kind of leave you hanging on the last one and let you do an example on your own, and that'll be one of the things we check in the notebook tomorrow. But first things first, if let's analyze the one-sided limits on 7. Let's do the limit as x approaches 7 from the left side, and then of course we'll do the one from the right side as x approaches 7 from the right side. So going back, when we do the left side of 7, we're looking for x is less than 7, and so this notation here tells us that we want to analyze this function right here and just plug the 7 directly into that. And that's going to give me, let's see, 7 minus 5 will give me a numerator of 2, and then 49 minus 16 should be 33. So 2 over 33 would be the intended height. And then for, let's see, approaching 7 from the right side, we're going to go x is greater than 7. Again, that equal sign, it means nothing to me right now. We might as well just throw it away. And I'm going to do a direct substitution, plug the 7 right into there. And let's see, we're getting 19 all over 36, I believe. 19 over 36. And again, we would then conclude that the general limit as x approaches 7 does not exist based on the fact that these one-sided limits were not equal to each other. All right, here's what I want you to do. I want you to try this one on your own. I want you to tell me what is the limit as x approaches -2 from the left side. X approaches -2 from the left side. This is kind of a fun question. It's more of a review question from something we did earlier in the video tonight, and it'll be a really good way to let me know tomorrow in class how we're doing on this particular topic. So way to hang in there, and we'll catch you tomorrow.